This video is about linear functions and slope, but we're calling this a review because this is in the context of an intermediate algebra course, and typically this topic is introduced in a class before this, though there is some overlap between all these algebra courses typically. So we'll call this a review. Now, in light of that, it's good to read and review any definitions provided in the textbook. We're going to just kind of jump right in and start using some of them in this video on this topic, that being a review. So you may need to review some of the formal definitions of things as we go along. Let's just dive in right with some examples where we want to find the slope of a line passing through, and then we have a couple examples. The first one says through the point -3, -4 and -1, 6. Well, you may recall that there is a formula to find the slope given 2 points. That would be m for slope equals y2 minus y1 over x2 minus x1. That's the slope formula. And then we'll go ahead and label these points. It doesn't really matter which one you call which. I'll just call the first one the ones, so x1 and y1. And the second one the twos, so x2 and y2. And then we'll plug the numbers in accordingly. So y2 minus y1 would be 6 minus -4 over, and then x2 minus x1 would be -1 minus -3. So of course we'll just do the arithmetic to simplify these. On top we have 6 minus -4, that's really 6 plus 4, which is 10. Down below we have -1 minus -3, that's really -1 plus 3, which would be a 2, which would simplify to 5, or 5 over 1. And so ultimately the slope of the line containing those 2 points would be 5. Let's try another one. This one's same kind of problem, except these points are given, the first one being 3/2, -6. So we'll call that first value, this first point, the x1, y1. The second point is 3/2, 1/6. So we'll call that x2 and y2. And then of course we're just looking for slope here. So we'll compute this using the same formula. y2 minus y1 would be 1/6 minus -6 over x2 minus x1 would be 3/2 minus 3/2. So you may start to cringe when you see fractions like this, but just give it a second. Try to take a step or two in the right direction and see what happens. In the numerator, of course, we'd have 1/6 plus 6. Now there's some fraction work to do there, but I'm going to avoid it for a second because look at the denominator. You have 3/2 minus 3/2, which would be 0, which means our slope as computed is some number, 1/6 plus 6, over 0, which we know to be undefined. So we'll go ahead and write it as that, undefined. That's the slope, which would really answer this question. Now let's recall, in light of that, while we're here, let's recall a couple important things. Number one, vertical lines have undefined slope. So in the context of this problem we just did, we found a slope to be undefined. Of course, that would mean that these 2 points we just computed here would be on a vertical line, you could say. But more than that, just another means of review here, let's say, secondly, that horizontal lines, so vertical and horizontal lines being like the 2 special types, you could say, horizontal lines have slope equal to 0. So that's another little review topic. Horizontal lines always have slope 0. Vertical lines have undefined slope. We'll just kind of see that showing up here and there as we do various examples. Now let's go ahead and try to review graphing a line, and we specifically want to use a certain type or way of doing it here. So this next example wants us to graph the following line. It's given as f of x equals 3/4 x minus 3. Now, you'll notice that this line is in what we call slope-intercept form. So the review of that specific form is not within the scope of this video, but that's a review topic as well, slope-intercept form of a line. I'm going to review it in the context of doing this example, but I'm not introducing this form. So you'll recall in slope-intercept form, this is the y equals mx plus b form. So for this example, we'd say m is the 3/4. That must be the slope of this line. And of course, the point 0, -3 would be the y-intercept. So the way that we can graph using this form would be to use those two pieces of information, starting with the y-intercept. If you plot it, so 0, -3, that's a point on the y-axis. And then from that y-intercept, you can count the rise and the run of the slope, knowing that it's a positive 3/4 slope, which means we would expect this line to be rising from left to right. So with a slope of 3/4, I could go up 3 and right 4 to drop another point. I could do that, of course, again if I wanted to get a few points to connect. And then once you get a couple points, you can go ahead and connect them to form the line, which would then be the graph of this equation. Let's try another example. This second one reads 7x plus 2y equals 14. Now you'll notice this one is not quite set up like the previous one in slope-intercept form. And we know that because y is not alone, which is typically how you understand slope-intercept form. So we're not going to go that route, though you could. You could do the algebra required to get y alone and then use slope-intercept form to graph this one. But we're going to do a slightly different method. Let's try. We're going to graph using intercepts. And this is another valid method to graph a line. You can use the x and y intercept as 2 points and then just connect them. And a function or an equation in this form is maybe more set up for this method. If we want to find the x-intercept, recall that means you set y equal to 0 and then solve. So we'll go ahead and do that. We'll copy this down as 7x plus 2 times 0 equals 14. Of course, this means 7x equals 14. Nice easy numbers, that's why it's a good candidate for this method. You divide both sides by 7, we would get x equals 2, which means the point 2, 0 is the y-intercept. So we can go ahead and plot that point and then just hold on and move on to the y-intercept, which of course is where you set x equal to 0 and solve for y. So we'll restart with the same idea. So we'll say 7 times 0 instead of 7x plus 2y equals 14. Of course, that really just means 2y equals 14. Divide by 2 on both sides, and we get y equals 7, which means the point 0, 7 would be our y-intercept. So we can go ahead and plot a point on that at that place. And then those two intercepts, once when connected, would form our line. So that's another way to graph a line, just by plotting intercepts. And then the way, the method you pick, whether it be slope-intercept form like the previous example or using intercepts like this one, just kind of depends on the way the equation is set up for you and picking the method that seems simple or simplest out of the options. Let's try another example. This next one says, find the slope of a line containing these 2 points defined algebraically. So this can be a little obscure at first. It says the first point is a minus b as the x-coordinate, comma c as the y-coordinate. And then the second point is a as the x-coordinate, comma a plus c as the y-coordinate. So instead of seeing numbers, which we may typically see, we're just seeing variables in place for the values of these points. It doesn't really change the process or structure of the problem, but it can be maybe a little more intimidating not to be working with numbers. Don't worry about it. Let's just go ahead and use the slope formula that we know, which is to label these x1, y1 and then x2, y2, just like we've been doing. And then we'll compute the slope for m equals, and then we'll just plug in the same formula, y2 minus y1. Of course, that would be a plus c as y2 minus y1 is c. And then x2 minus x1 for the denominator would be a minus, and then in parentheses here, a minus b. We had to use parentheses because we were subtracting a two-term expression, which would require the distributive property. So let's go ahead and simplify this. In the numerator, you have a plus c minus c. Well, those would combine and simplify just to a. And then down below, this would be a minus a, and then minus negative b. Well, don't forget to distribute the negative sign to both those terms. You'd end up with a minus a, which cancels out, but then you'd have a negative or a minus negative b, which is just a positive b. So altogether, a over b would be our slope. And of course, that's represented with variables given the way that this problem started. Now let's also recall a couple things. Slope is positive if the line is increasing from left to right, or you could say rises from left to right, or a slope is negative if the line falls, or you could say decreases from left to right. Those are just some general properties of slope to recall from that definition. Let's go on and try another example. This one gives us a chart, and then this chart, of course, is labeled to describe literacy and child mortality. It's a scatter plot. Okay, you don't really need to know a lot about scatter plots for this example, but that's what it is. It has a bunch of points randomly put on, not randomly, but just scattered throughout this graph. And they're just showing the comparison between the percentage of adult females who are literate on the x-axis, and then on the y-axis is the under 5 mortality. Now, the only thing we really need to know, which is described in this example here, is provided in the diagram. This example says use the y-intercept from part A and the slope from part B. Okay, well, we actually kind of skipped those parts. We'll just kind of ignore that. We have enough provided in this chart. We're just going to ignore the first part of that one. Says this one says write a linear function. Here we go. Write a linear function that models child mortality, f of x per 1,000, for children under 5 in a country where x% of the adult women are literate. So that's describing what's already labeled in this chart, which means we want to basically just get the equation of this line. And it's provided, well, what we've been given in the chart are these two coordinates that we can use. One of them is a y-intercept. That's the point 0, 254. And then the second point is not an intercept, but it's just a point on the line. It's the point 60, 110. Now, if that's what we're given, and we want to find pretty much the equation of this line, of course, it doesn't really tell us exactly which form to use. We could use slope-intercept form, y equals mx plus b, or we could use point-slope form. We'll probably just shoot for slope-intercept form because we're given the y-intercept as part of this chart, the point 0, 254. It's good to note that because that means that b is 254 if we're using slope-intercept form. Well, what we would need, though, to finish it off is the m, or the slope, right? To fill out y equals mx plus b, we already have the b, we need the m. So let's go ahead and compute that, and we can do that given 2 points. Well, what do you know? We have 2 points. I'm going to go ahead and label the first one. I'm just saying first as in left to right here, this top one. I'll call that x1, y1. That's the y-intercepts here. I'm going to call the second point the x2, y2. And given 2 points, we can plug them in the slope formula to compute the slope. We'll say y2 minus y1, so that would be 110 minus 254. And then down below, we'll also compute x2 minus x1, that would be 60 minus 0. Okay, so now we'll just need to simplify this fraction or compute this fraction. It would end up being, let's see, on top we'd have negative 144, and down below we'd have 60. And so if we simplify that or just kind of reduced that down, it would end up being negative 2.4 if you just kind of reduce that even with a calculator or something. And in that case, we have enough to fill out this slope-intercept form. We could say now y equals negative 2.4, that's our m. Okay, so that negative 2.4x, and then plus b, where b is given as 254, as we've already noted. So that would be the slope-intercept form of our line, negative 2.4x plus 254.